The last topic we will look at in section 3.4 is the linear factorization theorem. Up to this point in the section, we've been given the equation of a polynomial function and asked to find its roots or zeros. Here, we're going to reverse that process. So we're going to be given the roots or zeros of the polynomial, and we'll be asked to find the equation. Now, there are two important properties that we saw with polynomial functions that I referenced in the lesson for this section. One, an n-degree polynomial always has n roots and will have n linear factors if you count repeated roots, say when the multiplicity is greater than 1, and counting complex roots. And if you think about it, we've been solving third-degree polynomials in this section. You've been finding 3 roots or solutions. That's what this property really speaks to. The second property is that if you have a complex root, they always occur in conjugate pairs. So when you have complex conjugate roots, if you have one complex number as a root, its complex conjugate with the opposite sign must also be a root. So remember, the generic form of the linear factorization theorem looks like this, where we'll express our polynomial as the product of these linear factors with our n roots. And they're referred to as these complex roots C1, C2, all the way through C sub n, depending on the degree of the polynomial. Now remember, when we talk about a complex root, real numbers are technically complex numbers. There's just no imaginary part. So don't think that the roots are always going to have an imaginary part with I. And I gave an example in the lesson, and I'll repeat it here. Again, in this process, we're going to be given the roots, and then we come up with the equation. So if we were given a polynomial with these roots, -3, -1, and 1, well, we would initially set up the linear factorization theorem around those roots. We would have 3 roots, and there would be a leading coefficient of some kind. And then x minus -3 would be x plus 3, x minus -1 is x plus 1, and x minus 1 would be x minus 1. So notice, when we factor our polynomials, like we have in section 3.2, if you had it in this form and I asked you, well, what are the roots of the zeros? If they're in this linear factor form, you would tell me that this root here would be -3, this root would be -1, and this root would be 1. So again, we're really just doing the opposite of what we normally do when we find those roots or zeros. Here, we're given the roots, and we set up the factors to find the equation of the polynomial. Let's look at example 6 on page 402 of your textbook. So they ask, find a 4th degree polynomial, f of x, with real coefficients that has -2, 2, and I as zeros, such that f of -3 equals -150. So there's some key information we need to pull out of that to get the problem started. The first key piece of information is they tell us the degree of the polynomial. A 4th degree polynomial, we would say degree n is 4. So that means we need 4 roots or 4 linear factors to set up our equation. Now, they've also given us these roots of -2, 2, and I. But notice we need 4 roots, we only have 3. Well, where's the 4th root? Well, remember, complex roots occur in conjugate pairs. So if I is a 0, that also means that its complex conjugate, or -I, is also a 0. So that's where we find that 4th root, and we see that complex conjugate concept come into the problem. The last piece of information is that f of -3 equals -150. We'll use this piece of information, the very last step, to solve for the leading coefficient, a sub n. So because we have a 4th degree polynomial, we need 4 linear factors, so generically that'll look like a sub n, and x minus c1, x minus c2, x minus c3, and x minus c4. And those values for the complex roots are right here, -2, 2i, and -i. So when we substitute those actual values into this expression, we'll get this. This would be x plus 2, x minus 2, x minus I, and x plus I. And again, if you look at just this step, if you identified, well, what values would make these factors equal to 0, it would be -2, 2, I, and minus I, which are all the roots that we're starting with. So we've identified our 4 roots, we've created our 4 linear factors. Now we need to multiply these factors out to eventually get the equation. Now, you always want to start here if you have any imaginary roots. We want to multiply these values together. So we want to multiply these terms. So we'll get f of x equals a sub n. If we multiply these two terms, this will really be x squared minus 4, but we really need to eliminate these imaginary terms. So we'll initially get x squared minus ix plus ix will cancel each other out, and we'll get minus I squared. However, remember, I squared is actually the value of minus 1. We don't want to carry this value in the calculation. So minus times minus 1 will be plus 1. So just remember that from your complex numbers. So eventually, we would actually get to this expression. Now let's multiply these two expressions out here. So now we'll get f of x equals a sub n, and we'll get an x to the 4th. We'll get a minus 4x squared and a plus x squared, which would be minus 3x squared. And then we'll get a minus 4. So we're almost to the end. Now we just need to solve for a sub n. To solve for a sub n, we need to use this piece of information that the text gave us, that f of 3 is minus 150. So the value of x will be minus 150. That will equal a sub n. And now x is 3, so where we see x here, I'm going to substitute the value of 3 where I see x. And so we'll get minus 150 equals a sub n. This will be 81 minus 27 minus 4. And this will be minus 150 equals a sub n times 50. And then to solve for a sub n, we really just divide by this coefficient of 50 on each side, and we'll find that minus 3 is a sub n. Now, to finish the problem and get the final equation, I'm going to go back to this step where we just had this expression a sub n times x to the 4th minus 3x squared minus 4. We now have the value of a sub n. So we will now use that value of a sub n to substitute into the expression here. So I have minus 3 times x to the 4th minus 3x squared minus 4. And then we just need to distribute that minus 3 across that expression. So we'll get minus 3x to the 4th plus 9x squared plus 12. And there is our final equation for the polynomial.